So the session is now yours.
Yeah, thank you, ma'am. So everyone can able to see my screen?
Yes, sir.
So in last session we discussed how to do stress analysis on T-beam, composite T-beam. So in this session I'm going to cover how to find a natural frequency and mode shapes of composite wing. So it's hands-on training. If you have answers, you can work side by side. So you just work on answers workbench. So same procedure what we have done before. So I'm going to use answers composite pre here. So you can find ACP pre in the component system. So click drag and drop here. So first thing we need to choose the material for our analysis. So in answers we will be having a default materials. If you don't have the material what you want, you can create your own material. There is an option for that. So mostly researchers they will do experimental analysis on composites. So they will get some experimental results. You can use those results to create your own materials in the ANSYS ACP. So now double click on engineering data. You will find an ANSYS ACP engineering data tool. So our default material is structural steel here. So I'm going to choose a composite materials. So for that you can click engineering data source at the top, right? If you click here, you will get engineering data sources. It's called libraries. So in these libraries, we'll find different material libraries. So I'm going to choose a composite material here. Once you choose composite material, these are the default materials you'll find in the outline of composite materials. You can see here. So these are the default materials. So in last session, I said how to create your own material. See here, if you want to create a new library, you can click here and you can create your own library. Or else, if you want to add some materials in the existing library, you can click this checkbox and you can come to the outline of composite materials. Here you can add your material. If you give some name, you will find the properties, right? You can choose your properties. Based on your properties, you can add all properties there, right? So I'm going to create an existing material. So in last session we used glass epoxy. In this session we will use carbon epoxy. So I'll use this epoxy carbon. So whenever your library is in edit mode, you can't add materials. So uncheck this. So you can choose your material. See your plus symbol, click on this, then you will get a bookmark. So I chosen epoxy carbon here, and then I will use one core material. You can use any core material, PVC foam or else honeycomb, whatever you want. Right here, I will choose honeycomb, and then I will use a matrix resin. If you want any new resin, you can add those resins, but mostly you'll use epoxy. So I'll use this epoxy here. So once you add these materials, you'll find the materials here: epoxy carbon, honeycomb, and resin epoxy. Now we had materials for our analysis. So once the material selection is done, you just move to project schematic. In project schematic, in geometry, right click on that. See, we have two options in ANSYS now in the new versions: new space claim and new design modeler. So I'm going to use design modeler here. So you'll find the notification at the bottom, left bottom, right? Always you can see there. So this is our design modeler. So I'm going to import a parasolid file. So for that, go to file and import external geometry file. Click on this and you can click the file. The .xb file is nothing but a parasolid binary file. So those files are from SolidWorks or CATIA, whatever you want, CAD software. So you can design your material structure there. So why? Because ANSYS is not that much good for geometry. So once imported, you can see here your geometry is imported, and you will find a flash symbol. So once you get flash symbol, you need to generate. So click on generate. So our blade is a surface body. So the first thing is, whenever you want to do a laminate, you need a surface body. So this is our blade. So our geometry part is done. So close this part. So now click on model. Once you click on model, you can see the properties at the right. So now choose your dimensions. I'm going to choose here mm. So double click on model. So meshing is very much important in structural analysis. The size of materials, whenever you go for a fine small size, you will get a fine results. But at the same time, you need a powerful machine to do that kind of analysis. So this is our model. So what we need to do, see here, you will find a question mark. See, our surface body is not perfect. So what we need to do, I am going to give a fake thickness 1 mm. So first thing, right click on mesh. See, you can do right click, or else you will find the options here, mesh control, right? You can go to sizing and select the surfaces what you want to mesh and apply. So whenever see here in details, you will get the options to select your materials. So I selected 3 geometry here, 3 faces are selected. So and then the important thing is, you need to give element size. So what is the size of your element you are going to divide your blade? So here your default, always whenever you will use meshing, you will get some default values. Here our default value is 3 mm. So I'm going to give 1 mm. And then go to mesh, right click on that and click on generate mesh. So our meshing is done. You can see the body, the blade. So what we need to do, we need to define the name of each and every section in the blade. So for that, I'm going to give a name selection. Here you can see the four cubes. One is point, vertex, or else edge, and surface and body. So I'm going to give select surface here. So click on all surfaces. We have three surfaces. Using control, click on three surfaces and right click on that. So at the bottom you will find create name selection. So here I will give the name as face and click OK. So and then this is the area where pressure is going to apply. So click on that, create name selection and give name as pressure area. It's just for your reference. You can give any name and then go to edge selection, click on edge and click here and here. So now right click on this, create name selection and give name as edge. So we defined three names here. You can see here the face, here three faces, one, and this is the pressure area and edge. So three faces are here. So you can do your mesh for each and every face separately. So I'm not going to do meshing. We have a lot of options in meshings. You can see here. You can see sizing and face meshing. It will help you for structured mesh, right? In sizing also, see here, we can go to element size or sphere of influence, or else number of divisions you will get. So many options is there. So you can do whatever the mesh you want for your analysis. So I'm going to delete this. So our meshing part is done now. So you can close your mesh. So now you can find a flash symbol here. So right click on that. So you can see here update. So whenever you get a flash symbol, you need to update your section. Click on update. See, it will take time. Why? Because I gave 1 mm element size. So if you give a big element size, it will take less time to compute. So now we are going to laminate our composite ring. So double click on setup. So you can see here, this is your element view. So this is our surface. So I'm going to create a laminate over this. So same procedure what we have done yesterday. See here. First you need to update your material. So right click on this last epoxy. Whatever material you have at the last, you click on that and click update. So next we need to choose our fabrics. So fabrics is based on whatever the material we choose before. So right click on this, create fabric. So we have material epoxy carbon. So epoxy carbon. So now go to material drop down box and choose epoxy carbon here. and you need to give a thickness. So I'll give 2 mm thickness and click OK. So if you want to check the properties, you'll go to analysis. You can find Young's modulus E1, E2 and shear modulus. You can click on OK. So click on apply. So you can find those properties and the values here. So it's so now right click on fabric, honeycomb spending. So we'll give honeycomb. So choose honeycomb. So choose the thickness of honeycomb. Click OK. So right click on this, click on update. So now our fabrics are updated. So now move to element sets. So whatever the name we have given in the model, you'll find here phase, pressure area and all elements. So right click on this and click on update. And one edge we gave. So right click on this and update here. So now you need to create a rosette. So right click on rosette, create rosette. So in last session we used parallels. Why? Because it's a T-beam. So here we can't use that parallel. Why? Because our structure is not a symmetric or else so it's unsymmetric body. So I'm going to use edgewise. You can see edgewise here. So click on edgewise and then we have edge already we defined there. So click on that edge. So once you selected that edge, you can find here a red mark. So it's selected. So based on this edge, we are going to make a laminate. So click on OK. So our rosette is created. Now update your rosette and then move to orientation selection. So right click on this, create oriented selection and then in the element sets, choose face here and then in the point, click on this point and click somewhere here and click your rosette and click OK and update your model. So I click on this, click on so we need to flip this up and click OK. It's not objecting. We'll check. So flip this, click on row set and click OK. So our orientation is updated. So once your orientation is updated, then click on modeling group. So click OK. So this is the crucial section in the laminate. So you need to follow a laminate code procedure. So if you want a symmetric laminate or else axisymmetric, or else you can give unsymmetric laminate, it's up to you. So what I'm going to do, first I will choose symmetric laminate. So create ply. So choose your orientation and then material. So first we'll give 0 angle, click on OK, and then right click on that, create ply after. So choose oriented and then material. So you can give the orientation 45, I'll give here, click on OK and right click on this, create ply after, choose your orientation and epoxy carbon. So now I'll give a minus 45, click OK and right click on this, create ply, choose your element, material, and I'll give 90, right? So we created a 4 layers here. So let's check how this 4 layers looks. So update this and go to section cuts, create section cut and click OK and update your section cut. You can see here, this is the 4 layer we created. So on top of this, I'm going to create a honeycomb, a core material. So right click on this modeling ply 4, create ply after, and then click orientation set and choose honeycomb and click OK. Now update this honeycomb and update your section cut. You can find the position of a core material here, right? 4 layers here and core material is here. So there is a lot of gap. You can find a gap between these layers and this core material. Why? Because the thickness we have given, we gave 0.2 for epoxy carbon and core material 2 mm. So there is a lot of difference. So that's why you'll find a gap between this. So now I'm going to create the other four layers on top of that. So this is symmetric. So what I'm going to choose, I'm going to choose the fourth one and copy and paste it here. Right click on fifth and paste after. And third one, copy and paste after. And second one, copy and paste after. And finally the last zero layer. So copy this and paste here. So now you will update. So you can see the fiber direction. So now I will update the section cut. So you can see, so we have totally 8 layers and one core material. If you want more layers, you can add layers by adding here. You can add. So you can see the direction. If you want the fiber direction, you can choose the ply fiber direction here. You can see yeah, see here. So this is our 0 and this is 45 we chosen and this negative, right? So this is our core material and here you can see the 0 and here. So you can see the fiber orientation. So everything you can see here. So this is our, we just gave modeling groups and we created a place. Now I'm going to create a solid model. So right click on solid model, create solid model and choose element set. So the element set is here, all elements. See, to bind all epoxy carbon and honeycomb, we will use a resin epoxy as a matrix. So click on resin epoxy and click OK. Now right click on this, click on update. Yeah. So now your material is ready. You'll be having a composite rotor blade or wing, whatever you want. So our ANSI pre-processing is done. So up to here, if you have any questions or something, you can post now or somewhere down, or else we'll move for the next section. We'll do static model analysis. Yeah, if you respond, it will be helpful for me to move. I don't know whether you are listening or not. Shall we move? So right click on this and click update. So now our composite wing is updated. Our pre-processing had been done. So now go to static structural. In the analysis, see here, you can find the analysis system. So in component system, we laminated a composite wing. At the same time, now we are going to do an analysis. So for that, I'm going to use static structural, click and drop here. So what here, I'm going to click and drop your setup on model. So transfer solid composite data and transfer shell composite data. So here we are going to use a composites solid data. So click on this. So we are going to do a model analysis. So for that we need a model analysis system. So here click on model analysis system and drag it and place it to our on model and solution. You can see two red box on model and solution. Click on that. So now double click on model in the static section. So before that I'll close this. It will be a little bit confusing. Yeah. So double click on model. So this is your analysis system. You can see here. So you'll find a model here at the same time a static structural. Right? So click on static structural. So first thing what we need to do, you can find here. So we need to fix, you need to fix our wing. So I'm going to fix this wing. So click on support, fixed support and click on this surface. See in the details of fixed support, you can click apply. So now our wing is fixed. So now go to loads. You can find pressure here or else in the analysis system, right click on this, go to insert and you will find a pressure. So I'm going to apply pressure here. So we already know this is where the pressure area. Click on this and click OK. And see here. So we need to give pressure. I'm going to give 0.004 megapascal. So now the static structural, we fixed our body and then we gave a pressure area. Now go to solution. So once click on solution, you'll find a deformation, strain, stress, energy and damage, etc. So I'm going to click on total deformation. Right? First we will check how the total deformation. So now go to solution, click on solve. So now this is our total deformation. This is total deformation for whole body. So what I'm going to use now, I'm going to check for each and every lamina what we created. So for that, click on solution, go to stress here, click on equivalent stress. So once you click on equivalent stress, you will find the details of equivalent stress. So I'm going to choose the ply where exactly I want the deformation. So for that, you'll find that files in the imported plies. So click on ACP pre, solid model and modeling groups. So we have created. First I will check the deformation is the last ply. So click on this and click apply. Let's solve this. You can see the deformation in the last ply, right? So at the same time we will check the deformation in the first ply. So click on solution, go to stress, click on equivalent. So I'm going to choose the ply here. We will choose the ply here. So click on apply and then go to solve and click on solve. So this is the stress of first and last ply. You can see this. You can see this is your last and this is your first ply. You can change, you can see the change. You can find the change here, right? At the same time, see here 109 megapascal, the maximum stress, and here 132. So each and every ply stress is varying. So we'll check for our core materials. So click on solution, go to stress, and here. So I will choose a core material. So click here. Fifth, this is our core, and apply and solve this. So now you can find the stress in the core material. Right, this is our core material and this is our ply. So for like that you can verify each and every ply individually. So you can check, you can do analysis. So how much stress is acting on that particular lamina. So now, so what we are going to do, our target is to find the natural frequency of that blade. So say you can, here you can see the animation also. So how the blade will act. So this is our core material and this is your lamina last and this, right? And if you want total deformation, so now we are going to calculate the mode. So for that, click on model, here analysis system, you will find the analysis system, click on this. So here you can see maximum modes to find. So you can choose your number of modes. So I will give here 4 modes. See we'll see the controls, output controls. The natural frequency is based on stress and strain. So I'm going to give stress and strain yes here. Yeah. So now click on solve. So model analysis. So go to solution. So you can find the 4 modes in the tabular data. See, frequency, first mode frequency is 116 and second 267 point something, and third is 584 and finally fourth is 876. So let's check how it behaves. So select all 4 modes, right click on this and create mode shape results. So once you create a mode shape results, you can see the total deformations. Total deformation 1, 2, 3 and 4. So now go to solve. So now you can see here, this is your first mode and second mode, third and fourth. So this is what a vibration will takes place in the composite wing. So vibration analysis is very much important. So now we had a symmetric laminate and we found 856 heads is the maximum in the 4 mode. If you want, let's check by changing the pressure. So go to pressure. I will give 0.04. It's 10, right? So let's solve this. Yeah. So now you can see the deformation. And here click on solution, go to solve. So you can find the mode shapes, right? So based on your pressure, your mode shapes will change. So if you want to generate a report here, if you click on this, you can generate the report. So you can see here, this is a geometry and right. So we can click. So if you want to do analysis by changing the laminates layers, so click on setup. So now go to modeling groups. So these are the layers we created. If you want to add one more layer, so create play after or before. If you want after, you can click after, you can click before. So create play before. So suppose I will give orientation, and then epoxy. Here I'll give some 90, I'll give just, right? And here create ply after, and go to orientation, epoxy carbon, and the ply angle is 90. So now go to solid model and right click on this and update. Now you can see a little big model. So what we need to do, you need to just update everything. So right click on this and click on update. So again double click on model. See, whenever you will give some changes, you need to reread. So click on yes. So now see here, you will get flash symbols. So we need to update everything. So if you go to solve console, so now we are getting error. Why? Because can anyone tell me why we are getting error here? Can anyone? So I just updated, but I am getting error here. Why? Because our geometry shape is changed. So whatever the boundary condition we gave before, it's all based on before laminate. So what I am going to do, I'm going to update everything. Go to static structural, click on fix support. Now choose this and click OK, and pressure, select, click on pressure area and apply, and then pressure is already given. So go to solution and right click on this, solve. So now you can see the deformations and equivalent stress. So same thing, you can go to analysis setting, right? Solution. Now you can solve this. So you can get mode shapes also. So now or the see frequency before it was somewhere around 870 something. Now 846 is 110, and right click on this and create a mode shapes and go to solve. So you can see the mode shapes of the layer one more is added. So this is the way we need to find a natural frequency and mode shapes of the composite bed or any other shapes, right? So up to here, if you have any questions, you can ask. I will tell you how to create a geometry, and I'll give one exercise for you, and how to make a laminate over a pipe. So if you have any questions up to this, you can post your questions in the chat box, or else you can unmute yourself and ask me.
Any questions from the participants? You can post.
Yeah, I'm going to create a different pipe now. So before that, if you have any questions in the composite wing, you can ask.
I think no questions.
Yeah, feel free to ask questions.
I think no questions,
Yeah,
Dhanajayan sir.
fine.
Yeah, we can proceed.
Okay. So if you want to save your model, you can save in the regular procedure. So what I'm going to do, I'm going to delete this. So or else you can create a one more and save it here. Same procedure. First you need to choose a material. Double click on this and go to engineering data source, composite material. I'll create now some more 395 gigapascal, and this time we no need core material. I'll just select two materials. So engineering data source. So now go to geometry, right click on this and new design modular. Okay. So see here in the design modular, we will be having five major parts here: the graphics window, tree outline, details view, and here task work, sun modeling. See, whenever you want to create a surface or solid or a line item, whatever, so you need to choose your plane. So I'm going to choose an XY plane here. So in the tree outline, so now go to sketching. Before that, I will choose units to millimeter, and here look at. So in sketching, I'm going to choose a line. So choose line. Once vertical click, Click horizontal. So 4 lines I created, and then go to modify, use fillet, and choose 2 lines and this 2 line. So now you can see in the details view everything. Now go to dimension, click on general. What is the software for preliminary and ANSYS program with animation? Sir, I can't get your question. Preliminary ANSYS program in the sense, Dr. Imanshu.
Sir, actually, what is the main programming ANSYS software? Means the primary, the preliminary one. Suppose someone is a beginner, then what is
Okay.
the primary software for ANSYS?
So as ANSYS, see, you no need to learn any other software. Whatever the software, you can go from scratch. So here we no need any programming language. So we are not going to work on background. You can see, I will show you the best way to learn answers from the answers help. See here. So click on answers help here. Here you can see the user guide. So if you want to learn CFD, so go to CFD and go to its user guide and you will find some tutorials there. So same thing, if you want structural analysis, ANSYS composite pre post, everything you'll be getting here. So what in back end you can see Python. See here. So scripting language they will use. They're importing just to connect with the database. They'll use coding languages, Python or else any other programming languages. So I will show here. So in the setup you can see. See, whenever you will learn, this is IPython console. You can see here. So this is your IPython console. So whenever you will create a model, so it will connect to the database. So it will create, it will take everything from the database and it will update. See, suppose I want to choose this layer, it will go and call that particular function to build your layers. So you don't worry about the backend. Why? Because ANSYS is not a backend software. It's user friendly. It's API, right? So you no need to worry about backend which programming. So to learn this, it's very simple. You can go for any tutorials in the YouTube for as a beginner, or else the better way is learn from the answer self. So you'll be having, or else Simscape, an university, they are providing a good tutorials for this. SIMCAFE, I think. So you can learn from that. So is that okay for you? What I have answered?
Okay, sir.
Yeah.
Yes, sir.
So double click on geometry. I'll close this. Yeah. So now go to dimension. I will click general here. So click on this line and this line and this line, and go to radius, select this and select this. Okay, already. So whenever you get a red symbol, it's over constraint. So whenever you, it's purely different from any CAD software. See here, your blue color represents a constraint. So now give dimension here. So I will give normal arbitrary dimensions just for understanding purpose. I'll give. Okay, I will do this. Okay. This is 16 radius. And I'll give this 16. We'll give a little bit length of this horizontal. This is also this. See now line is chosen. So I give dimension. Now go to sketching and modeling. Go to choose ZX plane and look at. Go to sketching and I'll choose circle here. I create some circle. Go to dimension, radius, and click this and give some radius. So now go to sweep and in profile select the circle, apply, and then in path go to that sketch, apply. So main thing is we need to create a thin surface. So click yes. At the same time dimension thickness should be 0. So click on generate. So this is the pipe. So we created, and then our geometry part is over. Here one surface body we have. So close this and go to model. Again you need to choose model and double click on this. So now same question mark you will find here. So give fake thickness. So mostly the procedure is common almost for every analysis. So why? Because these are already predefined. See, answers is predefined. Everything is predefined. So we are going to give our own dimensions and we are going to do analysis. So same procedure. So right click on this, go to insert, sizing. So using control, you select all face, right? Go to apply, right? So here you can give the default material I'll give 5 here. So generate, right click on mesh and click on generate. See here, if I give 5 mm, you can see here somewhat is good, but this is not a fine mesh. So what I am going to give, right click on this and go to face meshing, choose this surface and this surface, apply and right click on this, generate. See here the face meshing is not working. So what we need to do, so face meshing is not suitable here. Right click on this and generate mesh. So you need to do analysis, see wherever you'll get error. So go to documentation and you can read through documentation. So same thing. First thing is import your geometry. First thing, make it into surface body and then measure geometry. Once you measure geometry, you need to define the name of that particular elements in the geometry. Why? Because the system should understand what is what, right? So go to edge sizing. So no edges. Select this face. Make it face, right click on this. View name as face. So go to setup now, update this. So now this is the make it as assignment for assignment or it's your own interest. I will tell you how to do analysis, right? So now you are going to create a lamina over this pipe. So for that, go to material data, same procedure what we have done. Go to fabrics, update materials, go to fabrics and see what is stack ups and sublaminates in the help session, and then element sets and rosettes, create your rosettes, then orientation. In modeling groups, you are going to give a play, right? And then section cuts is used to check whether the layer is correctly built or not. And then you are finally are going to use solid models, right? So you try in your system. So up to here, if you have any questions, you can post now. You can unmute yourself and you can ask, and or else ping me in chat box. I think mostly everyone are doctorates. Even I can't answer your questions. Don't bother about that. Once the question is raised, anyway, you'll get answer from anywhere. If I can't answer, you can get answer from somewhere. So please post your questions. You can unmute yourself and you can ask questions. See, if you didn't raise your voice or else your messages, I don't know whether you are listening or not. Is there anyone? Please post your questions. Yeah. No questions, Ravi Shekhar. Okay. What about others? Any questions? Yeah, Ravi Shekhar, can you unmute yourself and tell me why you don't have any questions?
Hello.
Yeah.
Yeah. Hello.
Yeah. Ravi Shekhar, can you tell me why you don't have any questions?
I'm not exactly working in this area, sir.
Yeah, fine. Okay.
So it was a nice presentation. Actually, I have used explicit dynamics for finite element simulation of metal matrix composite machining.
Okay.
That was also 5 years back. So
Okay.
right now I'm working in a different area of composites.
Okay.
So nice, but not exactly into model also. I've never done anything in vibrations also.
Okay.
Fine. It was a nice presentation, but regarding this area, I really don't have much questions.
Yeah,
Thank you.
Thank you, Singer. Yeah.
Yeah.
So I think mostly everyone are from different domain. I don't know whether this session is helpful for you or not. At least you tell me whether it is helpful or not, or else tell me in which area you want any sessions.
Uh, Participants can pose their questions. If no questions, like which area like you want to cover next time if the session is conducted.
Yeah, mostly everyone are researchers. Maybe you have done lot of research. You can share your knowledge also at that particular area domain. If you don't have any questions, you can expose your knowledge where you are currently working. At least I will gain some knowledge from you.
Yeah. Hello, sir.
Yeah.
Yeah. Thank you, sir. I mean, it's the first time that we are also being asked to post our views about something. So, I've been working in composite for some years now,
Okay.
and I was basically dealing with machining. and various mechanics while machining of nano and micro composites. And now latest is what we are trying now is to, because modeling is so difficult,
Yeah,
this is so
why? Because
dynamic.
we need to train machine, right?
Yeah, exactly. So what we are coming up now with, we are trying to apply control theory that is applied in electronics professors,
Okay,
electronics discipline, and
okay,
trying to use control theory equations like transfer functions and all to carefully model this machining systems of composites,
okay,
and then also to control it. For example, for
okay,
automation, what we need to do is, let's say I want my surface roughness to not rise above 1 micron while machining some composite. Okay,
okay,
so I need to model the system using a transfer function, uh,
okay,
control theory, and then based upon it, I can apply some controllers like PID, fractional order PID, or any advanced controller, and tune those controllers so that the input parameters, let's say cutting parameters or machining parameters, so let's say even we can take material parameters also,
okay,
depending on the experimental design, those are
okay.
controlled automatically in such a way that the output is always 1 micron.
I have one question, Mr. Ravi.
Yeah, please.
So during creating control systems, so how material is challenging? What are the challenges you faced in choosing the material?
Actually, materials were chosen long back, sir. Actually,
Okay,
that data is being used now for control systems.
okay.
When I took the
See,
materials, I took
I will give
carbon
some
nanotube.
example.
Yeah,
If I choose aluminum, so for
yeah.
that some it needs some controls, right? If I change that material,
Oh, yeah. Okay,
suppose it is
okay.
composite, it physical properties will change. So for that
Yes,
physical
yes.
properties, uh, is there
The
any
output will change.
struggle? Is there any challenge you faced in coding or transfer functions?
Uh-huh. Sir, actually, what happens is there are two ways of modeling the system. One is going through a fundamental way,
Okay,
and the second is maybe going through system identification approach, where we have the inputs and outputs parameters ready, and we
okay,
work in a black box approach. Let's say, I'll give an example. Let's
okay,
say we have a machining system where the output is, let's say, surface roughness or tool chip interface friction or material removal rate or anything, any machining process you take. Okay, and input parameters, we have some cutting parameters. You can take EDM or ECM or turning or CNC turning or milling or anything. Now, based on the parameters that we varied, all of those, like the experimental design in mechanical
okay,
that we do, design of experiments, all those input parameters and their levels, they come under input multi-input system, and we can have a singular multi-output system. Among those input systems, one can have materials also. Now,
okay,
we have not designed the control system as yet that could control, that could manipulate input variables of material properties,
okay,
because practically when we put into, let's say, when we are putting into industry,
okay,
what the control system is going to do, it is going to continuously measure the output. In this
okay,
case, let's say the output is surface roughness. As soon as it measures some output, that wherever it is, zero point 0.5 micron or 10 micron or 5 micron, wherever it is, it will try to manipulate the input variables automatically, the cutting parameters or machining parameters, in such a way that 1 micron is achieved, and it remains stable at that. What
okay,
we generally do is, we have the input and output values, and we have a mathematical model like regression or anything, or through
okay,
Taguchi or so many ways. And then we say, okay, this is how we establish a mathematical relation between inputs and outputs
okay,
through second order or first order, whatever kind of equation. And then we can say optimize it, and this is the minimization or maximization problem. So these are the parameter settings at which you get the minimum surface roughness, maximum tool wear, those kind of things. But
okay,
when we put it in industry, it is the other way around. Electronics people work other way around. Say, we have to fix the output to what you want, and the input
okay,
variables are automatically manipulated in such a way that the output is achieved no matter what.
okay,
That is what happens in automation. So that is for that we need firstly transfer function, because these regression equations are not understood by controllers. We need transfer functions many times, and other functions also in control theory, to firstly model the system in terms of those multi-input or single output or multi-input multi-output systems. And then we have to put them into controllers, and then controller parameters have to be tuned so that this kind of controlling action is performed. Now the same thing can be done in hardware also.
Okay.
So the next step, so this is first is simulation. We try it in simulation, then we actually connect it. So the next part will be to actually control, let's say, speed or feed or something basic, and actually monitor the surface roughness through a sensor, or maybe a cutting temperature, or anything, or toolware or something. And then actually the controller has to change the speed, feed, or depth of cut of or any machining parameter in runtime, in real time, so that the surface roughness remains at that 1 micron level. That is towards industry 4. And even this is the beginning. I mean, there is much more scope in this. So
Yeah.
we have now come in this direction. So
Okay. Thank you, Ravi.
in fact, we also presented a paper in MLRIT's conference in June this year, and
Okay.
we got the best paper award also.
It's
Uh,
very good. Good
it
name.
was, I think it was no, it was not on surface roughness. It was on tool chip interface friction. So we are working in this area. It's very interesting, sir. I mean,
Yeah.
now when you say machine learning also, you mentioned.
Yeah.
So what we are now doing is to improve that learning. See, we
Okay.
need our models to better and better.
Okay.
Generally, I don't receive much better accuracy, more than 60-70% for nano and micro composite machining
Yeah.
prediction.
Mostly now all companies they are using data science and machine learning to
Yeah.
predict uh,
Yes.
the material behavior, how it's going to behave in the future.
Yeah.
Yeah.
Exactly. So then now latest we have right now only. I mean, so latest. I mean, last past month, 1 month or 1.5 months, we are trying. We have
Yeah.
in fact implemented also machine learning
Okay.
in control system. Machine learning in control systems. I mean, in modeling also, for predictive
Hmm.
modeling, also in tuning the parameters of the controllers is in such a way that very good response and very good modeling characteristics are achieved. So
So
yes,
you have
machine learning
also
invariably
knowledge
comes in.
in machine learning also.
Yes, sir. It has to.
Yeah.
See, this is like multidisciplinary. We have to incorporate interdisciplinary. In fact, even in our conference, our reviewers, not reviewers, the
Okay.
session chairs were very happy to see that we, for example, when you talk to electronics guys about machining, they don't understand.
Yeah.
When I talk to them now, I'm turning. They say, whether are you turning left or turning right? I said, no, we're
Yeah.
turning the other. They don't understand. They have these people, the circuit branches. They don't know what happens in mechanical industry and actual machines.
Yeah.
We have to tell them this is the output. And when they
Okay.
say when they simulate, we have to tell them physically this kind of output is not possible. You can't have feed at 20 or something. They don't understand the physical implications of how much feed rate or depth of cut will cause damage to my tool and things like that. So we have to tell them, no, you have to be in these limits. Physically, you can't exceed these limits. It will be dangerous. So like that, we have to tell them, and they also learn about the actual systems in machining in industry, and we
Yeah.
mechanical people know it. And then we take their knowledge of control systems and try to have a kind of marriage between the two, so that in future we can have an automation, we can have industry 4 in some kind, and that too for composite materials. It is so exciting.
Yeah.
And then we can try different materials.
Okay. Thank you very much, Ravi.
Yeah, no, thank you, sir, for giving me an opportunity. I mean, you are the first speaker who has done this, so hats off to you.
Thank you. Thank you, sir. Any other questions, participants?
So any other questions or any other things participants wants to share,
If you
they
want to
can
share, you
share.
can share.
Yeah, because we are coming to the closure of the FTP and tomorrow is the last day. It's time
Okay.
for the participants to speak, sir.
Yeah.
And thank you, Dhanajayan, sir. You have taken that step
Thank you.
towards
Thank you,
making
ma'am.
them speak.
Any questions?
I think no.
Or else if you want to share something which is related to composite materials,
Yes, sir, sure.
yeah, you can share.
You want me to share?
No, no, I am asking participants. Mostly
Participants.
some of them, they may working, right? If they
Yeah.
want to share anything, they can share.
So I think there's nothing to share with the participants. It's really very helpful, sir. Nice session. Thank you. Thank you, Mani, sir. So live sessions are always like they keep you on hold. It's good to have a live session.
Okay.
Yeah. So,
You are,
so thank you very much, Dhanajayan, sir, for your
thank you,
time.
ma'am.
Yeah.
Shall we wind up or
Yeah. We'll
we'll
wind
wait for
up, sir.
someone to ask question?
We'll wind up because no one is like
Okay,
asking
okay.
any questions. If
Thank you very
anything
much,
is,
ma'am. Thank you, everyone. Thank you, MLR, for giving this opportunity.
yes, sir.
Thank you,
Th-
ma'am.
Thanks.
Thank you, sir.
Yeah, thank you.
Thank you, Ravi, sir, also for
Yeah,
sharing your views,
Thank you,
your
ma'am.
work. Yeah. And tomorrow you will have, it's your time. So we'll have whatever you want to share, you can share.
Yeah.
Thank you. Thank you very much, sir.
thank you, ma'am.
See you all tomorrow at session 10 o'clock. We have two
Okay,
speakers. One is from IIT Mandi,
okay,
Dr. Amir, and the other is from IIT Bhilai, Dr. Jose Emmanuel.
okay.
So we have two IIT professors who are coming tomorrow for the session and winding up. Thank you very much, sir.
Thank you all.
Yes,
Thank
with
you.
this we come to the end of the session.